On the morning of June 15, 2024, British Airways Flight 286 was just another long-haul crossing of the Atlantic. An Airbus A350-1000, one of the most advanced commercial aircraft ever built, prepared to depart San Francisco International Airport for London Heathrow. The aircraft was barely a few years old. The crew was experienced. The weather was calm. Nothing about the flight suggested that it would soon become a case study in modern aviation survival. Passengers boarded with the usual expectations of a transatlantic flight. 8 to 10 hours of quiet boredom. Movies, meals, sleep. Outside the aircraft, ground crews completed their final inspections. Tires were checked visually. Landing gear doors sealed. No alarms, no warnings. At 11:34 a.m. local time, Flight 286 began its takeoff roll. The A350 accelerated smoothly down the runway. As the aircraft reached rotation speed, the nose lifted. Seconds later, the main landing gear left the ground. And in that exact moment, unnoticed by everyone on board, one of the aircraft's wheels detached from the landing gear assembly. It did not explode. There was no fireball, no violent shudder. The wheels simply broke free. High-speed runway cameras later showed the wheel bouncing violently across the concrete, then lifting into the air before crashing through the airport perimeter fence and coming to rest near an employee parking lot. On board, nothing felt wrong. No warning lights illuminated. No abnormal vibrations reached the cockpit. The Airbus A350 climbed into the sky carrying over 300 people, missing a wheel. This is the story of how a modern passenger jet lost a critical component at takeoff and still flew more than 5,000 miles safely across the Atlantic. And why, under slightly different circumstances, it could have ended very differently. As Flight 286 climbed through 10,000 feet, the cockpit remained quiet. All systems indicated normal. The Airbus A350's flight control computers continuously monitored hundreds of parameters: engine performance, hydraulic pressure, structural loads. But none were designed to immediately flag a missing tire. Commercial airliners are not built with single points of failure. Each main landing gear assembly carries multiple wheels. On the A350-1000, each main gear has 6 wheels. Losing one does not automatically compromise structural integrity. In theory, the pilots followed standard climb procedures, unaware that a wheel assembly was now lying miles behind them. Meanwhile, on the ground at San Francisco, airport personnel were discovering something was wrong. Security cameras captured footage of debris crossing restricted areas. Ground staff were alerted. Maintenance teams located the detached wheel. Its damage pattern suggested a structural failure rather than foreign object impact. This was not debris from the runway. This wheel had separated under load. The airport notified the airline. British Airways operations contacted the flight crew. The message was brief and unsettling. A wheel from your aircraft may have detached during takeoff. Inside the cockpit, the pilots processed the information carefully. There was no emergency indication. No checklist for this exact scenario. Not yet. The A350 was stable. Fuel burn was normal. Cabin pressurization unaffected. The aircraft was already hundreds of miles offshore. The decision was made to continue the flight to London. For the passengers, the next several hours passed normally. Meals were served. Cabin lights dimmed. Most people never knew anything unusual had happened. But beneath the calm surface, the flight was now operating in a rare and serious abnormal condition. Landing gear systems are designed to handle extreme stress during takeoff and landing. Each wheel absorbs massive energy, hundreds of tons of force during touchdown. Losing one wheel shifts those forces unevenly across the remaining tires. The danger was not immediate. It would come at landing. As Flight 286 crossed the Atlantic, engineers at British Airways and Airbus began analyzing the situation. How much additional stress would the remaining wheels experience? Could the landing gear retract and deploy normally? Would braking remain effective on touchdown? The Airbus A350's design philosophy assumes redundancy. Losing one wheel is survivable. Losing two begins to approach structural limits. Losing more can become catastrophic. Flight 286 had lost exactly one. Still, every landing gear failure is treated seriously. At Heathrow, emergency services were quietly positioned. Fire crews staged alongside the runway. Medical teams stood by. But the airport did not declare a full emergency. There was no evacuation plan activated. The goal was a controlled, normal landing. As the aircraft descended toward London, the crew ran through modified landing procedures. Reduce landing weight, lower touchdown speed, smooth braking. Avoid sudden directional changes. The landing gear deployed. No warnings. No abnormal indications. At 6:56 a.m. local time, Flight 286 touched down on runway 27L. The aircraft rolled smoothly. There was no collapse, no fire, no panic. The Airbus A350 slowed, exited the runway, and taxied to the gate. Only after the engines shut down did passengers learn what had happened. A wheel had fallen off their plane at takeoff. For aviation investigators, the story was just beginning. The detached wheel was recovered intact enough for analysis. Early findings pointed toward a failure in the wheel hub or mounting hardware, stress fractures, metal fatigue, a defect that escaped routine inspection. The aircraft was grounded for detailed examination. Inspections extended to other A350 fleets worldwide. Regulators reviewed maintenance intervals. Airbus issued technical guidance. The incident did not result in fatalities, but it exposed a truth about modern aviation. Even the most advanced aircraft in the world can lose critical components without immediate warning. And sometimes, survival depends not on heroics, but on engineering margins quietly doing their job. This flight should not have survived on luck. It survived because of design. And because the failure stopped just one step short of disaster. The aircraft involved was a British Airways Airbus A350-1041, commonly known as the A350-1000, one of the most advanced long-haul passenger jets currently in service. Powered by two Rolls-Royce Trent XWB-97 engines, it is designed for ultra-long-range routes, capable of flying more than 8,000 nautical miles without refueling. It is built with carbon fiber reinforced polymer wings, advanced flight control systems, and a landing gear assembly engineered for redundancy. On that morning in 2024, the aircraft departed London Heathrow bound for a long-haul destination across the Atlantic. Weather conditions were stable, visibility was good, runway conditions were normal. There were no known mechanical advisories restricting dispatch. The takeoff roll began like thousands before it. Thrust levers advanced. The Trent XWB engines spooled up, producing over 97,000 pounds of thrust each. Acceleration pressed passengers gently into their seats. At approximately 150 knots, the captain called V1. Seconds later, rotate. As the nose lifted, and the aircraft transitioned from ground roll to climb, something happened that no one inside the cabin could see. One of the main landing gear wheels, weighing roughly 100 kilograms, detached from the landing gear assembly during the takeoff phase. It separated from the axle and fell back toward the runway environment. Inside the cockpit, there was no catastrophic alarm. Because the Airbus A350's landing gear system is built with multiple wheels per bogie assembly, the loss of a single tire does not immediately trigger a flight-ending warning. Aircraft of this size typically have multiple wheel configurations specifically to distribute weight and maintain structural tolerance if one tire fails or deflates. The crew continued the climb. Gear was retracted. The aircraft climbed through 5,000 feet, then 10,000. Passengers were unaware that one wheel was no longer attached to their aircraft. Back on the ground, airport personnel discovered debris near the runway. Initial identification confirmed it was an aircraft tire component. Ground operations quickly began tracing departure records. By the time confirmation reached operational control centers, the aircraft was already well into its transatlantic flight. Here is where the story becomes both technical and extraordinary. A fully loaded Airbus A350-1000 can weigh more than 300 metric tons at takeoff. The landing gear system is designed to absorb enormous vertical loads during landing, forces far greater than those experienced during climb. But losing a wheel changes landing dynamics. Landing with one missing tire increases load concentration on adjacent wheels. It can increase brake temperature. It can alter ground roll stability. In extreme cases, it can result in gear collapse if structural integrity is compromised. So why didn't the aircraft immediately divert? Because aviation decision-making is based on risk evaluation. By the time maintenance control analyzed the situation, several factors were considered. The aircraft had multiple remaining wheels on the affected landing gear. The A350 is certified to handle certain tire failures. Fuel state and alternate airport options were evaluated. Structural sensors showed no abnormal gear indications in flight. The crew was notified of the situation while en route. Imagine hearing that message. You have lost a wheel during departure. At 35,000 feet, over the Atlantic, the cockpit does not panic. Checklists are referenced. Engineering manuals are consulted via operations control. Landing performance calculations are revised. Emergency services are notified at the destination airport as a precaution. The aircraft continued for nearly 5,000 miles. Hours passed. Passengers watched movies. Cabin crews served meals. Turbulence reports were minimal. The aircraft systems remained stable. But as the destination approached, tension increased, not in the cabin, but in the cockpit and on the ground. Airport fire and rescue units positioned along the runway. Foam trucks staged. Medical teams alerted. Runway inspection teams prepared. Landing weight was recalculated carefully. Fuel burn had reduced mass significantly since takeoff. That reduction in weight would reduce landing stress, a critical factor. The aircraft began descent. Flaps extended incrementally. Landing gear deployed. Inside the cockpit, the crew monitored gear indication lights carefully. 3 green lights. No abnormal gear vibration warnings. Final approach stabilized. Speed controlled. Descent rate steady. From the cabin, it felt like any other landing. The wheels made contact with the runway. There was no explosion, no collapse, no runway excursion. The aircraft rolled out normally. Emergency vehicles followed closely behind as a precaution. The jet taxied clear. Passengers disembarked, unaware that global aviation forums were already discussing the event. Post-flight inspection revealed the missing wheel on the main landing gear assembly. Investigators began examining the axle components, retaining hardware, and torque specifications. In modern aviation, parts are traceable down to manufacturing batches. Maintenance logs are digitally recorded. Torque values are specified with exact tolerances. Preliminary findings pointed toward a possible installation or mechanical retention issue rather than structural design failure. Airbus A350 landing gear systems are supplied by Safran Landing Systems, engineered with fail-safe tolerances. Even with a missing wheel, the bogie beam structure distributes load across remaining tires. This redundancy is not accidental. It is the result of decades of engineering evolution shaped by past accidents. In earlier eras of aviation, a landing gear failure often meant catastrophe. Today, certification standards require aircraft to demonstrate survivability under partial gear degradation scenarios. This flight became a real-world example of those standards working exactly as designed. But it also raised uncomfortable questions. How did the wheel detach? Was it a maintenance oversight? Was there undetected fatigue in the retaining hardware? Were inspection intervals sufficient? Regulatory bodies reviewed documentation. Component manufacturers reviewed torque procedures. Airlines reviewed maintenance training protocols. No fleet-wide design flaw was identified. Instead, it became classified as an isolated mechanical event, serious but contained. And that is perhaps the most fascinating part of this story. Hundreds of passengers crossed an ocean in one of the most technologically advanced aircraft ever built, missing a piece of critical hardware, and never knew. Aviation safety is often invisible. Redundancy, design margins, procedural discipline, engineering foresight. They exist quietly until the day they are tested. This was that day. The Airbus A350-1000 continued flying in commercial service after inspection and corrective maintenance. The airline issued statements emphasizing safety compliance and cooperation with investigators. In the broader aviation community, the incident reinforced a powerful truth. Modern aircraft are not designed to avoid failure entirely. They are designed to survive it. And somewhere over the Atlantic, at 35,000 feet, a wide-body jet proved exactly that. The wheel fell. The aircraft did not. And that difference is the story of modern aviation. But to understand why this moment matters, why a missing wheel did not become a disaster, we need to go deeper. Long before this aircraft lined up on the runway in London, before the passengers fastened their seatbelts, before the engines spooled for departure, the safety of that flight was already being shaped by decades of engineering lessons written in metal and fire. Modern wide-body aircraft, like the Airbus A350-1000, are certified under some of the strictest safety regulations in the world, EASA in Europe and the FAA in the United States. During certification, landing gear systems are subjected to extreme stress tests. Engineers simulate hard landings beyond normal operational limits. They analyze brake energy absorption, side load tolerance, and single-wheel failure scenarios. The landing gear is not simply a set of wheels. It is a complex assembly composed of shock absorbers known as oleo struts, torque links, side stay braces, bogie beams, axles, brake packs, hydraulic lines, and multiple redundant tires. Each main gear assembly on the A350-1000 carries 6 wheels. Losing one does not eliminate structural integrity. It increases stress, but within certified tolerance. Every tire installed is documented. Serial numbers are recorded. Installation torque is measured precisely. Maintenance engineers follow detailed task cards. A retaining nut secures each wheel onto its axle. That nut is tightened to a specific torque value, and often secured with a locking mechanism designed to prevent rotation. Investigators reviewing this incident focused heavily on that retention system. Was the torque within specification? Was the hardware replaced during a prior inspection? Was there evidence of metal fatigue? In aviation, answers are not based on assumption. They are based on metallurgical analysis, maintenance documentation, and component traceability. While the investigation continued, the aircraft itself underwent deep inspection. Non-destructive testing methods such as ultrasonic scanning and dye-penetrant inspection were used to detect microscopic cracks. Engineers examined the axle threads. They evaluated wear patterns. They analyzed brake assemblies adjacent to the missing wheel position. Nothing indicated catastrophic structural weakness. This is the invisible layer passengers never see. Behind every flight is a system designed not just to prevent failure, but to absorb it. Consider the physics of landing. When an aircraft touches down, vertical forces can momentarily exceed several times the aircraft's weight. The oleo struts compress, converting kinetic energy into hydraulic resistance. Tires deform slightly, distributing load across the runway surface. Brakes generate immense heat, often reaching temperatures exceeding 500 degrees Celsius during heavy stops. Now imagine that system missing one wheel. Load shifts to adjacent tires. Brake energy redistributes. Stress concentrations increase. Yet because certification standards demand margin beyond normal conditions, the aircraft can tolerate such a scenario, provided landing performance is carefully managed. That is why fuel burn mattered. By the time the A350 approached its destination, it was significantly lighter than at departure. A reduction in mass directly reduces landing energy. Lower energy means lower stress. Lower stress means greater safety margin. The crew likely calculated landing distance using performance software, factoring in potential asymmetric load and brake distribution. They would have selected a longer runway if available. They would have requested emergency services on standby. These are not signs of panic. They are signs of discipline. The descent itself would have been normal in appearance. Passengers looking out the windows would have seen clouds giving way to coastline. Cabin announcements would have sounded routine. Seat backs upright, tray tables stowed. But beneath the cabin floor, the landing gear doors opened. Hydraulic actuators extended the main gear assemblies, each bogie locked into place with mechanical over-center braces. In the cockpit, gear indication lights confirmed extension. 3 green. The crew would have visually cross-checked parameters. No abnormal vibration warnings. As the aircraft crossed the runway threshold, descent rate steady at roughly 700 feet per minute, the pilots prepared for touchdown. Main gear contact. In that fraction of a second, thousands of kilograms of force transferred through the landing structure. The remaining wheels absorbed it. The aircraft remained aligned. Brakes engaged gradually. Reverse thrust deployed from the Rolls-Royce engines. There was no swerve, no collapse, no fire. Just a wide-body jet slowing safely to taxi speed. It is in moments like this that aviation's layered safety philosophy becomes visible. Redundancy, inspection, training, design margin, operational discipline. Each layer compensates when another is imperfect. Historically, landing gear failures have been among aviation's most traumatic events. In the 1980s and 1990s, several high-profile incidents involving gear collapses led to significant regulatory reform. Structural reinforcement standards were revised. Inspection intervals were tightened. Maintenance documentation became more digitized and traceable. The A350 represents the culmination of those decades of improvement. Composite materials reduce structural weight while maintaining strength. Electronic monitoring systems provide real-time data to cockpit displays. Brake temperature sensors track heat buildup. Yet even with all this sophistication, aviation remains dependent on human precision. A torque wrench must be calibrated. A mechanic must follow procedure. An inspector must verify installation. Most days, that system works flawlessly. On this day, something slipped, but the system around it held. In the weeks following the incident, aviation forums and industry analysts debated the implications. Was this a maintenance anomaly? A manufacturing tolerance issue? A rare but acceptable mechanical event within certified risk boundaries? Regulators examined whether additional inspection advisories were necessary. Airlines reviewed their own maintenance records for similar aircraft. Component suppliers conducted internal audits. The outcome did not trigger fleet groundings or emergency directives. Instead, it reinforced a quiet confidence in structural resilience. Passengers often imagine aviation accidents as sudden, catastrophic events, but the truth is more complex. Aviation safety is statistical. It anticipates the unexpected. A wheel falling from a wide-body aircraft during takeoff is dramatic. It is rare. It is alarming. But it is not automatically fatal. And that distinction separates modern aviation from its early decades. Today, commercial aviation operates with a fatal accident rate measured in fractions per million departures. Millions of flights occur safely every year. Most passengers never think about the engineering beneath them. This incident became a case study, not of failure, but of resilience. A reminder that even when something goes wrong, the system is designed to prevent escalation. As the aircraft returned to regular service, maintenance teams documented corrective actions. Replacement hardware was installed. Inspection protocols were revalidated. Life in aviation moved forward. Another departure, another climb, another ocean crossing. Yet somewhere in that story remains a powerful image. A 300-ton aircraft accelerating down a runway. A wheel separating and falling behind. A jet climbing into the sky, incomplete but uncompromised. It is a story not of disaster, but of margins. Of design decisions made years earlier. Of engineers who anticipated what might happen. Of crews trained to manage what does. And ultimately, of a system that proved stronger than a single missing part. Because in aviation, safety is not the absence of failure. It is the ability to survive it. And for nearly 9 hours across the Atlantic, that philosophy carried hundreds of lives safely home. 000, the aircraft lines up on the runway. Engines stabilize at takeoff thrust. The cabin vibrates as nearly 170,000 pounds of composite and aluminum begin accelerating down the runway. 0040, the nose lifts, main landing gear still firmly on the ground for a fraction of a second longer. Then liftoff. 052, positive rate confirmed, landing gear lever moved to up. Seconds later, a violent vibration. One wheel separates from the landing gear assembly. It drops toward the runway below. Inside the cockpit there is no immediate catastrophic failure indication, but there is abnormal vibration data. The crew senses something is not right. 0130, initial climb continues. The aircraft is airborne and stable. However, the missing wheel changes landing calculations instantly. 010, ATC receives notification of debris on runway. 03, the crew is informed of possible wheel separation. Silence in cockpit. From this point forward, everything becomes calculated risk. The Airbus A350-1000 uses a 6-wheel main landing gear configuration per side. Each wheel assembly is certified under extreme structural testing, including load factors exceeding operational limits. Each wheel is rated to endure speeds beyond 200 miles per hour at rotation and absorb landing forces that can exceed 1.5 times the aircraft's weight distribution across gear sets. A single missing wheel does not cause structural collapse, but it changes brake distribution, heat dispersion, load transfer, tire burst probability, landing roll distance. Engineers must evaluate asymmetric stress patterns, because if the aircraft lands with uneven force, structural bending loads could exceed tolerance in milliseconds. This is why long holding patterns often follow such incidents. Fuel must be burned, weight must be reduced, data must be analyzed. Commercial pilots are trained for engine fires, cabin depressurization, hydraulic failures. But rare anomalies create a different stress. There is no clear checklist titled, "Wheel missing after takeoff, severe structural risk." Instead, pilots revert to principles: fly the aircraft, analyze the data, slow everything down. In high-stakes aviation events, heart rate can spike above 120 BPM, yet voices on cockpit recorders often remain calm, controlled, almost detached. Because panic spreads faster than fire. United Airlines Flight 232, 1989, DC-10, catastrophic hydraulic loss. Qantas Flight 32, 2010, Airbus A380, uncontained engine failure. Delta Flight 191, 1985, microburst wind shear disaster. In each case, survival depended not on perfection, but discipline under chaos. Wheel separation incidents are rarer, but they are not unheard of. In 2010, a Boeing 777 departing San Francisco suffered landing gear component failure. Returned safely. In 2023, a Boeing 777-200 lost a tire during departure from San Francisco. Debris damaged vehicles on the ground. Aviation never forgets these moments. Each one updates procedure. Each one modifies inspection cycles. Each one tightens tolerances. Controllers now face a moving variable. An aircraft potentially compromised. Fuel load high. Runway condition uncertain. They clear airspace, delay departures, coordinate emergency vehicles. A single aircraft can reshape an airport's entire operation in seconds. Hours later, fuel reduced to safer landing weight. Runway inspected. Emergency services in position. The aircraft descends. Landing gear down. Confirmation shows incomplete wheel set. There is no turning back. Touchdown speed is calculated precisely. Main gear makes contact. Load transfers across remaining wheels. Braking applied gradually. Heat builds rapidly. But the structure holds. The aircraft slows, stops. No fire, no collapse. Just silence and relief. Following incidents like this, manufacturers review wheel hub metallurgy, bolt torque procedures, maintenance documentation clarity, inspection frequency cycles. The FAA and EASA analyze component fatigue data across fleets. Because aviation does not rely on luck. It relies on iteration. Every anomaly becomes data. Every scare becomes prevention. From the outside, it looked like a mechanical failure. But aviation is not defined by what breaks. It is defined by how systems respond when something does. An aircraft lost a wheel at takeoff. It did not fall from the sky. It did not erupt in flames. It did not become another tragedy. Because redundancy worked. Because training worked. Because engineering margins held. Modern aviation is not safe because nothing goes wrong. It is safe because when something does, layers activate. In the span of seconds, thousands of design hours are tested. And sometimes they pass. The aircraft landed. Passengers walked away. And somewhere inside hangars and engineering offices, the quiet work of improvement began again. Not dramatic, not visible, but relentless. Because the sky remembers every lesson, and aviation never stops learning.